guys, always know it's usually not a very good thing for a large table. But if the table is small, a full table scan is okay. But for very large tables, full table scans are bad. Bad, bad, bad. So, guys, here we go. Let's come back here. Let's look at a few things that we learned here, right? We saw something about a child table and the primary key. Then we saw something on the parent table. Let me kind of give you guys something. Just some little information here, which you can scribble down, may be meaningful sometime. So there is something, a table called a parent table. And there will be a table called a child table. What's the big difference between this? The parent table usually has the PK. Who knows what I mean by PK? Anybody? By PK, I mean
Parent key.
primary key.
Primary key.
Yes. Maybe I should actually take this. You guys don't seem to get it. A parent table has a primary key. And a child table has a
Foreign key.
foreign key. That's how they get related. Okay? So the whole idea is that the foreign key could be this. Let's see if maybe we go a little bit further. You could have a table like this, guys. Let's assume this is a table of 3 rows. And you have ID column, product name, price. And we call this, let's call this the product table. Then it's a big store that they're selling stuff, right? Then they have an order table. Means when somebody buys the product, they're going to put listed in this table. Let's assume that. So you have the ID of the product, you have the product name, and maybe the price too. But this one here is a child table. Therefore, this column of product ID, as a matter of fact, they won't have product here anymore. Let me take this out. So instead, they may have, let's say, quantity. quantity of the things bought, right? You just put something like that. So the way this whole thing works, right? Foreign key and primary key is this. The order table, you cannot order something that is not in the primary, that is not in the products table. So let's say we have product number 1, number 2, number 3, number 4. Those are the IDs. And somebody comes and they buy product number 1. Or say they buy product number 4. It will be written here. And the other things will be written here. And the person buys product number 5. But the person who wants to buy product number 6, they're going to go to that product table and they're not going to find it. So the whole idea is that that column works with that column. Or maybe the reverse. This column, whatever is, 1 second. Whatever is in this column down here comes from that column at the top. You cannot enter an ID down there that is not up there. Therefore, order table is a child table. So it has a foreign key. We'll just call it the FK column. And then this one up here would be the primary key column. You see? So those two work together. Cool. Anyway, let's move on to the next thing. Let's go to the next side of the stuff, and let me move. I need to see what I need to read and what I don't have to. I have to let you guys go do some reading. And this diagram that I'm drawing, right, is what we're going to study. We're going to study later on, right, something called the ERD. I know we talked about that before. Entity relationship diagrams. So that's what those diagrams up there would be. The ERD shows relationships between tables. In other words, the foreign and the primary key constraints. They are what actually make the ERD work. But still okay. Now, guys, let's move on a little bit faster. A second circumstance where indexes can be used is for sorting. So, guys, whenever you're sorting, indexes are used. A select statement that includes order by. So, guys, I want you guys to see this. This is what you could find in your exam. So, guys, any select statement that contains order by, group by, or union, these select statements would sort. So you must sort the rows in order, unless there is an index which can return the rows in the correct order without needing to sort them. Cool. Let's see the next thing. A third circumstance when indexes can improve performance is when tables are joined. But again, Oracle has the choice. So depending on the size of the table and memory resources available, it may be quicker to scan tables into memory and join them there than to use indexes. So guys, everybody put a star on your notebook on this, on your textbook, so you can read this later on. There is something called a nested loop join. What is a nested loop join? So the nested loop join techniques passes through one table using an index on the other table to locate the matching rows. This is usually a disk-intensive operation. Then there is a hash join. So these are different types of joins that we're going to study later on. There is a hash join. What is a hash join? They say this technique reads the entire table memory, converts it into a hash table, and then uses a hashing algorithm to locate matching rows. This is more memory intensive. So like that, memory intensive. Then there is another kind of join called a sort merge join. This one sorts the tables on the join column and then merges them together. This is often a compromise of disk, memory, and CPU. If there are no indexes, then Oracle is severely limited in the join techniques available. Indexes assist select statements, and also any update, delete, or merge statement that use the where clause, but they will slow down insert. I want you guys to catch this. Indexes, right, can slow down insert. Actually, they will slow down insert statements, but they assist select statements. So that's why too many indexes in a very busy table can be a bad thing. Now let's study types of indexes. There are different kinds of indexes worth knowing, guys. This is one chapter that I would recommend. We will read this chapter over and over because it applies to all databases that are relational in nature. Oracle supports several types of indexes, each with several variations. The two types of concern are the B-tree index. No, let me highlight that with a different color. So there's the B-tree index, guys. What does it do? Which is the default index type? So the B-tree is, so by default, guys, you create any index, it's a B-tree index. B-tree index. And the other type is called the bitmap index. This little section here, guys, you got to remember this. As a general rule, indexes will improve performance. Yep, that's just the general rule. For data retrieval, but reduce performance for DML. You guys catch that? This is because indexes must be maintained. Every time a row is inserted into a table, a new key must be inserted into every index of the table, which places an additional strain on the database. Yep. So guys, indexes, DML does not like indexes, but queries, selects, love indexes. For this reason, on transaction processing systems, it is customary to keep the number of indexes what? Low. So guys, oops, you get me a strange color. You see, on transaction processing systems, what do?
We keep indexes low.
Yep, not too many indexes. Too many, like, transaction processing is like your banks, grocery stores, Amazon shopping. Those are all OLTP. Perhaps no more than those needed for the constraints. And on query-intensive systems, such as data warehouse, to create as many No, to create as many as might be helpful. So guys, some places, right, you have to reduce number of indexes. Some places, if you're dealing with a data warehouse, oops, I could have highlighted that with a different color. So on data warehouse, create as many indexes as possible. But on OLTP, remember we should call that OLTP, keep number of indexes to bare minimum. Now let's see that index type called the B tree. What is the B tree index? Which is the default index type? The B tree index, guys, and catch that. B stands for balance. That's why they call it the B tree, right? It is a balanced index. And they say it is a tree structure. It looks like a tree for real. The root of the tree points to nodes at the second level. Yep. Which can point to nodes at the third level and so on. The necessary depth of the tree will be largely determined by the number of rows in the table and the length of the index values. So guys, there is something about depth in here. The necessary depth of the tree is determined by what? Determined by number of rows. Cool. In other words, this B tree index, could think of it looking at something like that, guys. And we have a root down there. Okay, so that's our little tree, the B tree index. So if you have it like that, the depth, oops, just 1 second. The depth will be this. That's the depth of the index. And we know, we just heard that depth has to do with number of rows. Cool. But nobody will ask you that, okay? The B tree structure is very efficient. If the depth is greater than 3 or 4, then either the index keys are very long or the table has billions of rows. You guys catch that? If the depth is greater than 3 or 4, then either the index keys are very long, or the table has billions of rows. If neither of this is the case, then the index is likely to benefit from a rebuild. So if your index is performing badly, right, and you don't see any of those two things, like it has billions of rows, or the depth is greater than 3 or 4, then know your index is fragmented and you need to rebuild the index. Cool. This explains a whole lot here. I used to go through this, but over time, I started to find I don't really have to torture my people through this. But with time, you may read this and it will make sense. Okay? Because when you come to read in here, you're going to see words like leaf nodes, pointers, which other word again? Equality predicates, the where clause, the between, even the like. Okay, but I won't go through this just now. Let's step down to one tiny little section that's important. Something about the row ID. The pointer to the row is the row ID. What is the row ID? And the row ID is an Oracle proprietary pseudo column, which every row in a table has. Encrypted within it is the physical address. So guys, encrypted within the row ID is the physical address of the row. Because row IDs are not part of SQL standard, of the SQL standard, they are never visible. So here, rows are never visible to normal SQL statements, but you can see them and use them if you want to. This is demonstrated somewhere. Okay, who really cares? So guys, I want you guys, everybody kind of mark this again. And right here, row ID. We need to know more about the row ID as we move forward. And we are told this about that same row ID thing. That row ID, guys, for each row is globally unique. Every row in every table in the entire database will have a different row ID. Yep, no two rows will have the same row ID in the same database. The row ID encryption provides the physical address of the row. Oracle can use this to calculate which operating system file and where in the file the row is located. Wow. All right, let's see if it's worth looking at this, my little diagram here. So guys, see what row IDs actually look like a little bit. I think it's worth it looking at this. So you wrap your head around this row ID concept. Select style from region. So guys, we write that query, right? It gives us 4 rows. Then, look at another select statement. Select row ID from regions. And of course, when you do that, it's a wise thing to add some different columns. Just to spice it up. Oops, excuse me. Picking the wrong thing to write here. So you can see. So if you look at the output, guys, look at the output. You see that row ID right here. Oops. Just 1 second. That's our row ID. And guys, see what the row ID looks like. It contains the physical address and everything about the row. Cool. Now, watch. You can write a query just using the row ID. Select star. Oops. So select star from regions where. Guys, see how the row ID is used here. Where row ID equals. And that row ID that I've picked here, if you look at it, it is that row ID up there. And when they do that, we get the right information. But if you look at this, it's exactly that row. So if you know your row ID, your queries can be super fast. Okay? But it will be painful just trying to find those. Let's go to the next section, next side of the thing, and just 1 second. Let me see what else. All right, B tree. B-tree indexes are an efficient way of retrieving rows. if the number of rows needed is low in proportion to the total number of rows in the table if the table is large. So guys, I want you guys to catch how many ifs are here. Guys, watch this. If the number of rows needed is low. The other one, if the table is large. So this B-tree indexes, guys, you use this when you have thousands or billions of rows and the table has too much data in it. So look here, let's see. I know I did some example here that I used to spend hours explaining this example. So if you look at this query here, guys, select count. We are reading from here. Select count star from employees where last name between, guys, watch that. Last name between A and Z. That means everybody, anyway. If you write this kind of a thing, right, Oracle just better go do a full table scan because you're taking all the rows anyway. The where clause is sufficiently broad in that it will include every row in the table. You guys see in this particular case here, it will include every row in the table. It will be much better, much slower to search the index to find the row IDs and then use the row IDs to find the rows than to scan the whole table. You guys catch that in this particular case here? After all, it is the whole table that is needed. Another example is that if the table is small enough that one disk read can scan it in its entirety, there is no point using an index. So guys, there's no point to use an index if your table is too small. And they have a rule of thumb. I could write here rule. Rule of thumb right here. The rule is right here. So guys, let's see what this supposedly small rule of thumb is. So guys, that if the query is going to retrieve more than 2 to 4% of rows, then a full table scan will be quicker. Hear that? Not even 40% or 22%. A special case is if the value specified in the where clause is null. Then there we see that nulls do not go into B-tree indexes. So a query such as the following will always result in a full table scan. So let's see here. It says select star from employees where last name is null. So in this case, Oracle just do a full table scan. Okay. I think what time is it? 9:46. This long chapter, guys. Sometimes I hate this chapter myself. All right. Let's read some other stuff here. There is a little value in creating B-tree index on a column with few unique values, but it will not be sufficiently selective. Let's read that line again. That there is a little value, only little value. Let's see what that is. In creating B-tree index on a column with few unique values because it will not be sufficiently selective. The proportion of the table that will be retrieved for each distinct key value will be too high. In general, B-tree indexes should be used if the following are true. So guys, Let's see here. So number one, when should we use B3 indexes? So this is a summation of the whole thing. Guys, when the cardinality in the column is high. Now, guys, what is cardinality? Can somebody tell us what cardinality is from this sentence? It's written right here. Number of distinct values. Number of distinct values is called cardinality. Number two, the number of rows in the table is high. And number three, the column is used in where? So guys, the column in question is used in where clauses or joint conditions. If not, don't use the B3 index. That's it. That's the whole idea, guys. When should we use the B3 index? It's all written right here. Let me box this out. When to use the B3 index. That's what that little section is all about. Is this clear to everybody? When they say the cardinality, a number of distinct values in the column is high. I want everybody to watch here. Number of distinct values. Who understands what it means by distinct values here? Oh, I hope the class didn't go home and I'm all by myself.
Unique.
I think it will be non-repetitive.
Yeah, non-repetitive. Or like unique, like you say. In other words, guys, cardinality, that's the number of rows in the column, is high. Number of, not just rows, distinct. In other words, guys, a column like, let me tell you guys what it is that you understand this right now. You're creating a table, right, for University of Maryland students. University of Maryland has 50,000 students. And you create a table and you create a table and you have something like first name or for example, student ID, first name, last name, middle name, gender, start date. Now, gender. Gender would have, how many types of gender are there? Anybody?
2.
How many types of gender?
Of course, 2.
That's 2.
Okay, let's say 2. Male, female, M and S. So if you have 1 million students, how many types of genders are there? 2, isn't it?
Mm-hmm.
Therefore, that column of gender is a column of low cardinality. But the column with student ID would be the column with highest cardinality. Because student column with last name, you may have 1 million students, you may have 10,000 that have the same last name. But student ID, no 2 students will have the same ID. So that column will be the column of highest cardinality. But those numbers are different. So guys, that's what number 1 here says. The cardinality, the number of distinct values in the column is high. Then create a B3 index. Number 2, the number of rows in the tables. So it is a table with thousands or hundreds of thousands or millions of rows. Number 3, the column is in the where clause. So the column, let's say you use the column, let's say it was you use student ID. you can use that, create a B3 index on student ID if you think that most where clauses would use student ID as their query definition. If most people say where student ID equals, then it's worth making student ID an index column, and a B3 index for that matter. Now, let's talk about the other index called the bitmap index. So guys, there are two types of indexes, B3 and bitmap. How do we start that B3 again? Just hang on. I'm trying to look. Oh, started it up. So guys, I want to write number 1 here, right? Put a star. Guys, better read that. Then let's go scoot down. Number 2, the bitmap index. In many business applications, the nature of the data and the queries is such that the B3 indexes are not of much use. Consider a table of sales for a chain of supermarkets that stores 1 year of historical data, which can be analyzed in several dimensions. And they have a figure here that shows a simple entity relationship diagram. So guys, this is, whenever I hear that word ERD, this is a typical example given of an ERD. You notice they have sales in the middle. It's related to channels, date, shop, product, and all of that. But there's a lot of history here. I won't read it. Frankly speaking, I will skip this section. Let's go straight to when do we use this thing. Bitmap index, this is all you need to know. In general, bitmap indexes should be used if the following are true. Number 1, the same point like we saw back there, right? Cardinality in the column is low. The number of distinct values is low, guys. The other one is high. The number of rows in the table is high. So it's a huge table also. But the column that you're creating the bitmap index on has a low cardinality, like a gender column, for example. Then the next one is the column is used in, guys, notice here, Boolean algebra operations. Let's see what the other one was. The column is used in a where clause. You guys see here? This other one here was that the column is used in a where clause or join. Then you can use a B3 index. But for the bitmap index, the column is used in a Boolean. Who remembers what Boolean is, or Boolean algebra operation? What is it? Who remembers what is Boolean? Anybody remembers this?
Two possible operations, true or false, where we can use it.
Yes. Sounds like that. Thank you. Hey, guys, whenever you hear Boolean, better remember. When they say Boolean, they mean true or false. So if a column, you're always going to ask people to say true or false because of that column. Then you want to put a bitmap index for that column. Cool. Yep. So that's the whole thing, guys. Let's go to, well, next thing, index types options. Index types. So guys, index, we've seen different types of indexes, right? The bitmap and the B tree. But now you have some options that you can give those indexes. And those different options would be, for example, guys, you can create an index, you make it unique or non-unique. Number 2, you can create an index, you make it a reverse index. Number 3, compressed, composite, function-based, and ascending or descending. Okay? So these are some choices you have when you're creating these indexes. And I think these ones here, these are bitmap. Indexes. Whereas B-tree can function with all of them. The B-tree index. Bitmaps are a little bit more picky. So, guys, these are 6, right? And they say all 6 variations apply to B-tree, but only the last 3 can apply to bitmap indexes. So now, guys, they tell you that an index is unique. What does that mean? What is a unique index? Unique index. Let's just go through this. So guys, a unique index means an index that cannot allow or permit duplicates. Non-unique is default. So guys, catch that. So by default, indexes are non-unique. The unique attribute of the index operates independently of a unique or primary constraint. The presence of a unique index will not permit insertion of duplicates. Yep. Even if there is no such constraint defined. A unique or primary key constraint can use unique indexes. There's some good stuff here, guys. So unique or primary key constraint. As you can use non-unique index. It will just happen to have no duplicates. This is the fact. Okay. Then let's go down a tiny little bit to a reverse key index. You create an index, you say it's reverse key. What does that mean for us? They say this one is built on a version of the key column with its bytes reversed. So guys, see an example here. They say rather than indexing JOHN, it will reverse it like NHOJ. That's what a reverse key index will do. All data that they put in is reversed. Cool. I'll skip the rest. Let's go down to the next section. What about a compressed index? This one stores repeated key values only once. So, for example, guys, if you create a bitmap index and you say it's compressed, right? And you have 1 million people, and the gender column has male, female, male, female, 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 male. A compressed index would install just 2 characters, MF, and even compress it again for that column. The default is not to compress. That's true. Meaning that if a key value is not unique, it will be stored once for each occurrence each having a single row ID pointer. A compressed index will store key ones, followed by a string of all the matching row IDs. Great. Then, guys, we're going to also create something called a composite index. So what is a composite index? Guys, this one is built on concatenation of two or more columns. That's what a composite index is. A composite index could be something like this, guys. We could create a table, right? Say this is our table. And we'll go inside this table. We give headings like, let's say, first name, last name, date of birth, let's say date of birth, last name, first name, date of birth. Let's
Gender. Gender.
Okay, let's say gender. Then we create our index like this, guys. We say create index on, we make our index to be this. If we create our index on that, then this would be a composite index. Okay, it has more than one column. You see that? So say create index.
Prof, would it be a compressor?
Let's
or
call
composite?
this table, I didn't give the table a name, did I? Let's say our table is called, let's say we call it the student table, contain names of all students. So we can take first name, last name, date of birth, we make it an index. If you do that, that index will be composite because it has more than one row involved. That's the whole idea, but a composite index. You're going to hear that everywhere in your life as a DBA. There are no restrictions on mixing data types. Yeah, when you do that, you can put different data types. If a search string does not include all the columns, guys, catch this. What we're selecting now, right, we did not include all those columns. Let us say, if the search string does not include all the columns, the index can still be used, but if it does not include the leftmost column, Oracle will have to use a skip. Catch that. Use something they call a skip scanning method. That is much less efficient than if the leftmost column is included. Leftmost column means the first column, right? Composite index. Then, guys, let's talk about another one called a function-based index. Function-based. And this one, guys, let's say it is, let's say this particular index is built on the result of a function applied to one or more columns, such as, I see a typical function in Oracle, upper. That will give you only the last name in uppercase. Or to car. We'll take date, I will change the date to characters. Okay? A query will have a query will have to apply the same function to to the search string, or Oracle may not be able to use the index. By default, By default, down here, guys, an index is descending. Right? So by default, an index is, ascending, not descending. And what does that mean that an index is ascending? Meaning that the keys are stored in order of lowest value to highest value. And what if they say the index, that it's a descending index? So descending index, you will be told here that it does, reverses this. In fact, the difference is often not important. The entries in the index are stored as a doubly linked list. So it is possible to navigate up or down with equal celerity. I like that word. But this will affect the order in which rows are returned if they are retrieved with the index full scan. All right, guys, so that's it about indexes. Know that, then, guys, let's create indexes, and then you'll see. The performance of every relational database hinges on its indexes. So we're going to study this, come back to this chapter, and I'll ask you guys to do these exercises over and over and over. So indexes are created implicitly. Guys, catch this. So indexes are created implicitly when a primary key and unique constraints are defined. If an index or on the relevant column does not already exist. So guys, an index can be created implicitly. Means without the intention, without you making a decision that I want to create an index. But because you create a primary key and it needs an index, Oracle will just create the index for you. The basic syntax for creating an index is index explicitly is as follows. So guys, so this is our index syntax. And when you create the index, people just look at this syntax. Often they look confusing, but if you look at it carefully, it makes sense. So it says create index. No, create. You don't use the word index here. If you watch, create, the word index is far up here. So when you do create, you have to decide whether I want a unique or a bitmap index. Notice, they did not say B3. They say unique. Because by default, indexes are B3. If you want it to be bitmap, you have to specify. So after that, they say the schema dot the index name, and then they go forward. They say on, and they give the table name, and it ends with a semicolon. And if you look at that table name, they go here. They do table name or schema dot table name. Then after that, they list the columns that they want. And they tell us here, the next line below, the default index is a non-unique, non-compressed, non-reverse B3 index. That's your default index. It is not possible to create a unique bitmap index. And you wouldn't want to if you could anyway. And indexes are schema objects. And it is possible to create an index in one schema on a table in another. So I can create an index in your schema. That's what they're trying to say here. But most people will find this somewhat confusing. A composite index is an index on several columns. Finally define it down here. A composite index is an index on several columns. Composite indexes can be on columns of different data types. and the columns do not have to be adjacent. So, another thing. They say many DBAs do not consider it good practice to rely on this thing called implicit index creation. If the indexes are created explicitly, so guys, you can do it explicitly. So if they are created explicitly, the creator has full control over characteristics of the index, which can make it easier for the database administrator to manage subsequently, because you can see the name of the index and know what it is meant for. Consider this example of creating tables and indexes and then defining constraints. So let's look at this thing here and then our long course or longest chapter. So people,
Prof,
yes.
yeah, as you were going along, I just wanted to clear my mind.
Yes, sir.
My understanding so far from the time you started describing the architecture and the block and the row, all those things, my understanding was that these indexes are generated kind of as we input data into the database. By default, the row IDs, all those metadata are generated by default. So create indexes, and when it says by default is the bitmap. So how useful is it like implicitly creating indexes? Because I got a little bit dragged behind. In my opinion, it was that this is databases work, and it will be easy for performance for the database to navigate whenever it is queried when it generates these indexes by itself.
The control that when you create a primary key without an index on the table, Oracle will automatically create an index.
And yes, that was my understanding.
It will give that index a system name, its own name, some long name that means nothing to you, the DBA. And it will put the index in the same table space with the table, which is a bad idea. So for very large tables that the indexes are truly used, you want to put the indexes in their own table space.
Yeah.
And if you let Oracle create the indexes for you implicitly, then you don't have control on where the indexes would live.
I thought all of them were in like this data dictionary.
No. An index contains data. So an index must belong to a table space to store its data. When I told you like the example that I did here, say assume this, right? These three columns would be extracted out of this table and put in the indexes table space in the index segment, because the index has segments. Remember one of these segment types, you saw that?
Yes.
Which is blocks, right? So this information will be put inside the blocks that belong to the index. So that when we're searching data, we go search by the index, we don't search on the table. Then once we find the information we need on the index, then using that row ID of that information that we have, we're going to come back to the table now and get the rest of the information.
The detail.
Yes, the details. So by default, most of the time, 90% of the indexes are single, they are not composite. They are on one column. And often the column that is here they call ID, product ID, student ID, part ID, whatever. We make that by default the indexed column. So, guys, let's watch here. It's so easy to create indexes, you won't believe it. So everybody, guys, watch here. If you never created an index, you're going to see it right here. So this particular note here starts by doing create table depth. So they're creating a table called department. Come on. Yep, they're creating a table here called department. And this table has 2 columns. As you can see here, it has 2 columns. So the columns are department number and department name. That's it. Because you can see it ends there with a semicolon. Then they create another table. That one now is called EMP. That's for employees. And that employees table has two columns also. Employee name and surname. No, it continues. And forename. And date of birth. And department number. Now I want you to watch. You see department number here? Would kind of match that department number. Just by me looking at this, I know the EMP table will be a child table to the department table, it looks like. Okay, then they start to do the indexes now. So now guys, watch. Create a unique index. And they give the index name. And they say on. When they do that on, if you notice carefully there, they give us the table name and the column name. So this index called department I1 on the department table column called department number. Let's see the next index. Next one, EMP, blah, blah, blah. Okay, it's about the same thing. Next statement. Then let's see the next one down. Okay, let's see the next statement. That one now is create index. EMPI2. If you notice, no, let me end just here. Then they give us name of the index and they tell us what table it's going to be on. Cool. Then next we'll see create bitmap index I3 on. We give that. Cool. Then alter table statement, the next statement there. Alter statement depth, add constraint, depth, TK, primary key, department, blah, blah, blah. I want you guys to take note of that. They're adding an index to the table after it has been created. Then the other one is alter table, add again. See, they're doing those add constraint. And this constraint is a primary key. The other one too was a primary key. Then the next table, alter table, EMP, add constraint. See, that one is a foreign key. That's a foreign key. But most importantly, the statement did not end. Because there is a foreign key on that column and references department. In other words, it references the parent table. So that is the parent table. But the employee is the child table. Cool. Then the guys that go below, they're trying to explain that whole thing, the yada, 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 which I was just trying to struggle and explain. So what I'll say is, I want you guys to read this. If my explanation didn't make any sense, read that whole thing for us. But I'll just highlight a few points here. Once created, indexes are used completely transparently and automatically. Before executing a SQL statement, the Oracle server will evaluate all the possible ways of executing it. Some of these ways may involve using whatever indexes are available. Others may not. Oracle will make use of the information gathered, okay, on the tables and the environment to make the most intelligent decision about which indexes to use. So guys, Oracle decides what index to use, not us. We'll create them because we know it's the right place, the right thing, and Oracle would end up saying, I don't like it, or maybe I use it. And the Oracle server would sit down here, should make the best decision about index use. But if it is getting it wrong, it is possible to for a programmer to embed instructions known as, so guys catch this, there's something called optimizer hints. So the programmer can embed those optimizer hints in the code that will force the use of certain indexes.
This is the impression I was giving, Prof. You know, in my mind, it was that if Oracle creates the index itself, because who uses the index is Oracle, not really us.
Whether you create them or not, right? Oracle use them. The only reason that we create that it is better for the DBA to create the indexes is to put them in the right place, the right table space where they should be, and to size them correctly. Because you may decide to create your indexes in a 2 KB block instead of 8 KB. Oracle will not do that for you. You have to do that yourself. Then once you create the indexes, Oracle can do anything on the column. It doesn't mind. It will not create those implicit ones anymore. Because the implicit ones are unrecognizable. Anyway, so guys, this is how you pass optimizer hints. You then write your select statement in here. It could be update or query or delete or whatever. Then you end it like this again. So whatever's in between those tabs is what the optimizer is going to follow. Modifying and dropping indexes. Let's look at this. Then 226. Yes. Let me just see how much of it. No, let's just finish this section. Yeah, finish this, then we can go. Hey guys, alter index command is a big thing. So the alter index command cannot be used to change any of the characteristics described in this chapter, including the type B-tree or bitmap of the index, the columns, and whether it is unique or non-unique. The alter index command lies in the database administrator's domain, and it is typically used to adjust. So guys, so what do we use alter thing for? It's typically used to adjust the physical structure of the index, not the logical properties that are of interest to developers. If it is necessary to change any of these properties, the index must be dropped. So most of the time, they have to drop indexes. Continuing the example in the preceding section, to change the index EMP I2 or 1-2 or 12 to include employees' birthdays, you must use blah, blah, blah. So guys, so typically this is how you change an index. You drop the index, and that's all about dropping it, eh? You simply say drop index and give the index name. Same as you're creating it, you create index. You give the name, you say on, you give the table name, and then you end with a nice semicolon. Okay. Next point. So up there, guys, this is a composite index. That's what I'm trying to say. Create index, they give the index name, and they give column 1, column 2, column 3. You see? So that is a composite index. Let's see if there's anything for me to highlight here before we end. The composite index now includes columns of different data types. The columns happen to be listed in the same order that they are defined in the table, but this is by no means necessary. When the table is dropped, all the indexes and constraints defined for the table are dropped as well. If an index was created implicitly by creating a constraint, then dropping the constraint will also drop the index. Let's catch that. So the big key thing here is the dropping constraints. If the index had been created explicitly, remember that one was explicitly, and the constraint created later, then if the constraint were dropped, the index would survive. Hope that makes sense to somebody. So you have an exercise here, guys. Create indexes. Play with those. Then tomorrow, we will tackle constraints. After this chapter, then our class would swing now through things that would be much easier, things that we don't have to spend too much time on reading. And I just point out the thing and you do the exercises. So let's call it, it's exactly 10:30. I'm going to call it quit for today. Let me see how far we've got to go. I'm on page 35 or 36. And we have, my God, I hate this chapter. Chapter makes me sick. So long. Yeah, but I think we'll finish it tomorrow. Yeah, I have to make sure I finish it tomorrow. We don't want to do this for more than 3 days. Because tomorrow will be the 3rd day on this chapter. And hopefully I don't go and I'm explaining stuff anymore. Cool, guys. So with that said, let's call it over for the night. And please spend some time this night if you're still fresh a little bit. Go to the classroom, open the PDF, and do the exercises up to where we are right now. So do the exercises up to here, where I just ended, okay? Yeah. Do exercises up to exercise 5-5. See that we've gone through half, right? And we've seen 5 exercises already. This tells you that, this should tell you that this is an important chapter. All right, people, thank you all and have a wonderful night. I'll look at the quizzes, and from the quizzes, I will see who is in our class and who is not.
Thank you, sir.
Yes, ma'am, Fube.
Sir, please, can you fix my machine issue for me?
Your machine is down.
Yeah.
Yeah. I remember saying that sometime you put something in the group. What is your machine number again?